So this last section is basically evaluating polynomial functions and looking at the real world situation. So let's go to the book. So the book has an example on page 570, and it's modeling a heart rate of an athlete. So here's the function that they're giving us. It models an athlete's heart rate, and so the pulse will be P, beats per minute, okay, and T is the minutes after the strenuous exercise is stopped, okay, and so it's going to go from 0 to 8 seconds. So what is the initial heart rate when the athlete stops exercising? Well, that's at 0. So at exactly 0, if we put 0 into the equation, we're going to get 200 beats per minute is what's actually happening there. So that's why they're putting in 0 in here and calculating it out. But what is the heart rate after 8 minutes? So let's do that. So if we do that equation, after 8 minutes, we're looking at P of 8, right? And then that's 1.875 times the 8, and that's to the second power. And then we're going to do 30 times 8, and that's plus 200. Okay, so what's going to be like after 8 minutes? Okay, so if you take your calculator and you did that, that would be 8 times 8, which is 64, which is 8 squared. So 64 times 1.875, and then subtract 240 from that, because that's what 30 times 8 is, and then add 200, you get 80. So now you're going to get 80 beats per minute is what you'll end up getting. And so that gives you the idea that after so many minutes, then the heart kind of goes back to its normal pulse rate. But then the last part of the question said, a graph of P is shown, interpret this graph. And so if we look back at this graph in the book, you see that after so much time, over time, the heart rate goes back to its normal heart rate. Here, from all that running, the heart rate is way up there at 200, but then it starts to slow down once it has caught up with everything. So that's basically it, and that's what they say on the next page. They say the heart rate does not stop at a constant rate. Rather, it drops rapidly at first, and then it gradually begins to level off. And that's kind of what the heart rate will do, is it doesn't do it in a linear fashion. So if we want, we can take a look at another example that's similar to that, which is problem 127 on 582. So we'll go to 582. Okay. And we're looking at problem number 27. So it says a heart rate of an athlete, the following table, the heart rate is at 100 meters per race. So the race lasts 10 seconds. Okay, and here's the table. And then they give us the equation, and they want to know, does this equation model the table exactly? Well, I went and did the calculator, and I put it in there. So we'll turn it on. So I put it in already, the 0.2x squared plus 5x plus 90. And then when I did second table, I compared, and yeah, the first one works, 0.90. But when you go to 2, it says at 100.8, where this is 100. And so a few of them are off. If I go to 4, it's 113.2. It says 113. If I go to 6, it's 127.2. It's 127. So even though at 8 minutes, it's 142.8. is what we're looking at. So the only one that was right was the first and the last one, I think. Yeah, 160. So does it model exactly? No, it does not. Does P provide a reasonable model for the athlete's rate of? Yeah, it does reasonably. It's close enough, I guess. It's just they're just dropping all the decimals, I guess. And then does P of 12 have significance in this situation? Well, I could do 12 here in the table, but the race lasts only 10 seconds, not 12 seconds. So there's no point in doing that. So what should be the domain of this particular equation? It should just be from 0 to 10. It shouldn't include the 12. And so that's kind of like, I think, kind of a little bit of a trick question there. But I just wanted to point that out because sometimes that stuff happens and you're not paying attention to that. And it could cost you something there.